Good morning, Algebra 2 classes. I hope you had a great Easter weekend or holiday weekend or however you celebrated this long weekend. And here we are back with the last week of the 6 weeks, meaning our grades are going to be posted soon. We have a test this week. It's going to be open from Monday through Thursday, that's for A day, and then Tuesday through Friday for B day. So it gives you about 4 days to work on this test. It does take a little bit of time. We will be working on it together in class, so just be aware. The notes that we're taking today are going to really help you through this process because it's taking all of the logarithmic function attributes and everything, and we're actually going to apply it to a fun little murder mystery, I guess you could call it. So anyway, let's go ahead and get started here for our log applications. We have learned, right, that an exponent is a log. So something that we've learned recently is log base A of n equals equals x is the same as me writing a to the x power equals n, right? So notice that we have talked about this before, and we're going to be looking at this when we're using our constant e. We've talked about e as being Euler's number. So we are going to look at this a little bit more of actually solving equations with our base of e. So let's look at what natural log is, and you can see it there in our notes here, how to write that, but I want to talk about what natural log is. Ln is actually the same thing as log base of e. So know that those are the same things, and when we're solving equations, especially with our constant e, that we can take the natural log of both sides and actually solve the equation much quicker. So let's look and see what this means. If I have Ln of n equals x, that is the same as me writing n equals e to the x power. Now, why is this? This is because Ln is the same as log base e. So if I were writing this like this, then that would make a little bit of sense of me saying e to the x power equals n, right? So when I take the log base e of both sides, then I can cancel those out. So we're going to see what this looks like in example 1. So follow along with me here. Example 1. We have a here, and it's e to the b minus 5 equals 51. So we're going to solve this by taking the natural log of both sides. So when I take the natural log of both sides, it actually cancels that e value out. So when I say ln of e to the b minus 5 equals ln of 51, just think of your algebraic rules here. Whatever you do to one side, you have to do the other. Well, it applies to logs as well. When I do that, these actually cancel, and so I have b minus 5 equals the natural log of 51. So we can go ahead and solve this by adding 5. And so b equals the natural log of 51 plus 5. So let's see what this is using our calculator. We can actually get a number here. Function ln 51, close your parentheses, plus 5, and we get 8.932. So we'll write b as 8.932. So I want to go back and think about this. When I take the natural log of something, right, I'm actually taking log base e of e to the b minus 5 power equals ln, or log base e of 51. So think about this statement here. When I take the log base e of something, I'm really saying e to the x, right? E to the x equals e to the b minus 5. Do you see how those cancel each other out? So in fact, when I take the natural log of E, it actually cancels out. So we can kind of see how that works. If you don't care about that, you just want to know the pattern, then know that when you take the natural log, it cancels here. That's your algebraic proof there. I think that's your discussion question too. Let's go to B here. Move my calculator. We have E to the P plus 8 power equals 88. So we're going to do the same thing. The natural log of E to the P plus 8 power equals the natural log of 88. Just like we proved before, those cancel each other out there. So P plus 8 equals the natural log of 88. Subtract your 8, and let's see what we get. The ln of 88, close your parentheses, minus 8 is negative 3.523. Negative 3.523. And we are going to get some negative numbers in our answers here, so just be aware that that's okay. All right, so C is negative 2 times E to the 5R power equals negative 32. So before I take the natural log of this, I'm actually going to isolate this E value by dividing by negative 2. You probably already thought that. So E to the 5R power equals 16. Now we'll go ahead and take the natural log of both sides. And we get 5R equals ln of 16 divided by 5 after that. R equals, let's see, natural log of 16, close your parentheses, divided by 5 equals 0.555. All right, so that's a quick lesson in our beginning solving logarithmic equations. Go ahead and try these. We'll talk about these in class. And we're going to look at how this actually applies to physics and Newton's law of cooling. So if you think about if you ever have a hot beverage, a hot tea or a hot chocolate or coffee, one of those things, how long does it take to cool down to room temperature? So know that, first of all, when you're thinking about laws of cooling, it's only going to cool down to the temperature of its surroundings. So if my room is 72 degrees, then if I have a cup of coffee, it's not going to cool down to lower than 72 degrees because that's the surrounding temperature. Makes sense, right? So let's look at this Newton's law of cooling. I'm going to pull it out pretty large here. And just the pieces. It's just a basic formula, but it's actually using our constant number E here that we've learned about. And you can see here, here's the formula, and then all of the items below here, pretty self-explanatory, where T is time, T of T is the temperature of the given object at a time T. So that's your outcome basically. Then T of S is the surrounding temperature. And T0 is the initial temperature of the object. You can think about that as your initial or starting temperature. And then K is the decay constant. So thinking about that as negative, decay, obviously think about that as a negative number, right? It's going down. You know, as we've looked at our transformations, that negative number in our exponent here with exponential functions actually makes it look like a decay formula, right? Or function. So let's look at what this is. Let's look at our example. We have a brewing pot temperature of coffee is 180 degrees. So it's starting out as 180 degrees, and the room temperature is 76. After 5 minutes, the temperature of the coffee is 168 degrees. So find an exponential equation to represent this situation. And then we're going to answer this question here. How long will it take the coffee to reach a serving temperature of 155? Here's our steps here. What you need to know for this formula is your decay constant first. So it helps to have those 2 points of on your function to know, just like if you were going to find slope, you have to have an x1, y1, and x2, y2. The same concept goes for this exponential function, is that if I want to find that constant, that decay constant, which it's exponential, so it's not going to be like a slope, you need to have those 2 points on your function to know what that constant number is. So that's our first step, is we're going to find that decay constant. And then we're going to use the decay constant to write a new equation, just like writing an equation of a line, right? It's all coming back to you. And then we're going to use the new equation to find the time it takes for the coffee to reach. So we're just going to go through those 3 steps here using our Newton's law of cooling. So let's look at, there we go. Let's look at our formula. I'm going to write it down first. So T of T equals T subset S plus T subset 0 minus T subset S again, raised or times e to the negative k T power. All right, so let's think about this. The brewing pot temperature of coffee is 180. So that's its starting temperature, right? So that means that the initial temperature of the object, that's what we're going to write for T of 0 is 180 degrees, right? And the room temperature is 76. That's your surrounding temperature, right? So it's going to be T subset S is 76 degrees. And then after 5 minutes, the temperature of the coffee is 168 degrees Fahrenheit. So our time here, time is 5, and our T of 5 is 168, right? So we're going to use all of these numbers first to find our decay constant, that K number there, right? So keep in mind what we've been practicing, taking natural log of both sides, we're going to actually be implementing it here. So our T of T, 168, that was T of 5 equals T of S is 76 plus T of 0 is 180 minus 76. E, that's our constant, minus K, and keep in mind that we're looking at time at 5 minutes. So we're using those 2 points when T is 0, right? Starting number was 0 at 180 degrees. And then after 5 minutes, it's 168. So we're going to use this to solve for this K value here. All right, so let's just kind of narrow our stuff down here and find out what all of this is. So we're just going to do our parentheses first, just like we should. 180 minus 76 is 104. So I have 76 plus 104 e negative k 5. And I'm going to rewrite that in just a second. Now I'm going to subtract my 76, just using my algebraic skills here. And 68 minus 76 is 92 equals 104 e to the negative 5k. I just rewrote it, multiplicative identity, and you can write them either way, right? Same thing. All right, so now I'm going to divide this by 104, just like we did with that negative 2. So I have a 92 divided by 104 equals e to the negative 5k. It's probably looking a little bit like the equations that we used at the beginning of the notes. So now we're going to do that ln. So we're going to take ln of 92 over 104 equals ln of e to the negative 5k. And remember, when you take the natural log of e, it cancels here. So we have ln of 92 divided by 104 equals negative 5k. And to solve for k, we're going to divide by that negative 5. So let's see what we get here. ln divided by 104. So that is in parentheses. Now I want to close my parentheses and then divide it by that negative 5. Let's see what we get. 0.0245. That looks pretty good. So our cooling constant here is 0.0245. 5. All right, so I want to take this value, this 0.0245, and apply it to my initial function, but I want to see how I can apply it to my initial function so it can apply to any time that I plug in here. So let's see. Instead of 168, I'm going to put t of t because I want it to be a function that I can apply to any time. The 76 stays. The 180 stays because that doesn't change. It started at 180 degrees, right? The e is still there. The negative is still there, except this number is going to be 0.0245 and t on the end. So notice I can put in any number of minutes here and figure out what that cooling temperature is going to be using this function. So let's read our question here. It says use the new equation. So there's our cooling constant. Here's our new equation, right? And now we're going to use the new equation to find find the time it takes for the coffee to reach the temperature of 155. So we're going to use this equation, and instead of t of t being 168 after 5 minutes, we're going to use 155 here and leave our t because we don't know what that time is, right? So let's move over here. We're going to use our function. Instead of t of t, we're going to say 155. This is probably looking familiar to you from solving the equation of a line, except we're using more advanced algebra skills here, 0.0245 and the variable t. All right, we're going to narrow all of our stuff again. So we know that this is 104, 76 plus 104e, negative 0.0245t, and 155. Subtract 76. I'm going to use my calculator because I don't want to get it wrong. You probably do the same thing, right? 155 minus 76. I want to know that I'm right. That's a 79 equals 104e to the negative 0.0245t. Divide by 104. So I have 79 divided by 104 equals e to the negative 0.0245t. And now comes our natural log piece. So we're going to take the natural log of both sides, 79 over 104 equals natural log of e to the negative 0.0245t. Those cancel, right? That's our algebra skills. So we have the natural log of 79 divided by 104 equals negative 0.0245t. When we divide by that negative 0.0245, we're going to get how long it took. So let's see. Natural log 79 divided by 104, come out of our parentheses there, and then divide it by negative 0.0245, 11.22. So our time here is 11.22, and we were seeing that in minutes, right? So let's see if that makes sense, right? After 5 minutes, it was 168 degrees. Does that make sense? So at 0 minutes, it was 180, right? That was our starting temperature. 5 minutes, it was 12 degrees cooler. And then 11 minutes, it was 13 degrees cooler than that. Does that make sense? Yeah, it absolutely does. So that tells us what the time that elapsed, not like 11 minutes after 6. It was the time that elapsed, right, after to get cooling. If you get a negative number here, that means that it was before. So keep that in mind when we're talking about our test today. All right, so we're going to do the next example together in class because I want to make sure to answer your questions that you have, and I'll see you soon.